thank you everyone for attending today. Welcome to, I guess this is the first ENERCOMP webinar series. Today we have, thank you for our speaker, Dr. Ilias from Imperial, and also all the guests and also the members of ENERCOMP. I think to start, maybe I would like to give maybe a few minutes to Professor Gilles Lubino as our director to maybe give an introduction.
Okay. Thank you very much, Aldi. So, Ilias, thank you very much for being here today as our first speaker. So, just to explain the context, so you know that ENERCOMP, it's a consortium that we started here at KAOST between KAOST and Aramco to develop new solutions for composite inspections and in-service monitoring. And we are very happy in this framework to introduce a new seminar series to disseminate a little bit the knowledge and to reach out to the community in these areas. So as you know, ENERCOMP has four main pillars. What we call tracks. So the first one that is about performance, the second one that is about inspection, the third one about sensing, and the last one that is about digital twin and digitalization. And what we will do is that every month, one of the track leaders in these tracks is going to take the lead to invite a speaker and to emulate some discussion in this area. So today we are discussing, the discussion will be led by Aldi, who is the track leader for the sensing and monitoring part, and he's going to animate this seminar. So don't hesitate to come back every month. You are going to get the invitation if you are part of SASCOM, if you are part of ENERCOMP, and if you are part of our circle at large. And don't hesitate to spread the word about this seminar series. Thank you. Ilias, Aldi, the floor is yours. Thank you so much.
Okay, thank you very much, Gilles. I think I would like to give the floor to Ilias, who will be, as mentioned, we will be starting the discussions with the sensing and monitoring track. And I think the topic of the presentation today about sensors, digital twinning on composite aircraft structures is pretty much in line with our track, let's say. So Ilias, it's the floor is yours. And also for anyone with questions, you can put it on the chat and then we can, discuss it afterwards at the end.
Okay, first of all, thank you very much, both to Dr. Aldi and Professor Lubino for arranging this and inviting me for this talk. I didn't realize it was the first one, so the pressure is really on me to make sure I kick off things nicely. So let me start by first sharing my screen. Can you see my screen?
Yes, we can.
Yes. Okay, so hello everyone. I'm Ilias Giannakeas. I'm a research associate at the Department of Aeronautics of Imperial College. And today I will be presenting my research on digital twinning entitled From Sensing to Safety, a digital twin framework for smart air vehicles. Now, the main presentation will be on a framework I've been working on the past couple of years, and specifically the different stages we require to go from our sensing data to actual residual strength predictions. Now, a little bit about me. My PhD is on metal modeling and specifically on fracture mechanics in brittle materials, where I used peridynamics to simulate fracture. And after my PhD, I joined the Structural Integrity and Health Monitoring Group at Imperial, that is led by Professor Aliabadi and Professor Padai, where I have been working on structural analysis, reliability analysis, and lately I have started also working on some new machine learning and AI and how we can integrate this to assist with the signal processing parts. So To kick things off, I would like to make a very brief introduction about what SHM and digital twins is. That is the basis of today's talk. And specifically, starting with structural health monitoring. What it is a combination of sensors and data analytics, really, to assess the integrity of a structure. And what we will follow a lot in today's talk is the SHM hierarchy, which starts with the detection to see if there is damage in our structure, localization of the damage, and characterization of the signals to see, okay, if we have a damage, how big it is. These three first steps define the diagnostics of SHM. Once we have completed our diagnosis, we can move on to the actual assessment of the structure, where we try to do a prognosis about its future state. Let's say we have a damage, so we have reduced the strength of the composite. Is it safe to continue operating, and what kind of mission profiles we can still use the structure, and if not, what may be corrective actions we should make. In the past decade, the booming advancements in IoT and computational power have actually made possible to have digital twins. Digital twins are really a combination of a physical system, so our actual structure with the sensing network, and a virtual system that contains all the models and analysis algorithms that are able to communicate with each other in a two-way approach. So there is information passing between both the physical and the virtual system between each other. And this communication is actually taken care of by the communication and data management components. And also we have a component for user interface, because at the final stage and the top stage of digital twin, what we want is to support decision-making by the users and the operators. So in reality, structural health monitoring and digital twinning actually go hand in hand in order to enable continuous learning, provide all the necessary information to the system about its state, and really put some context behind the sensor estimations. So the vision with this with a framework on that combines SHM and digital twin is really to be able to achieve on-demand indicators and assess in real time the integrity of the structure. If we achieve these things and we integrate them in the design phase of the structure, we can actually relax safety factors, while during operation, we can actually avoid the current schedule-based maintenance and transition to a purely condition-based maintenance. So this is the vision behind all this research. And the aim behind of today's presentation is to really present a holistic framework that we try to valorize our data. So what we try to do is pretty much close the loop. We start from our sensors, we extract our signals, we process our signals, we translate all the features and indications we have extracted into reliability estimates, and these reliability estimates actually assist the decision making. Of course, there are challenges, and we will discuss them in more detail during the upcoming slides about how we address, for instance, environmental differences or data scarcity and uncertainty in our system. But the most important thing is what benefits that this is going to give us. The frameworks like this can be adapted to different industries, but for aviation specifically, we can reduce maintenance costs that account for almost 20% of total operating costs, improve safety by having early warning systems, and lead to lightweight structures that can assist with the green transition and really enhance the sustainability of aviation. So how we're going to do this? What we are going to discuss today is pretty much having two building blocks that operate in parallel. One building block is on the mechanical behavior of the structure and how We can start from simple structures and really propagate information as we go to progressively more complex structure and reach our target structure. At the same time, we have in parallel investigations that try to quantify the response of the SHM system. These responses start again at the coupon level, and as we propagate through the building block, we push the information to the higher scales. This will give us a combined data set of a lot of experimental investigations that will be combined with our physics-based model in our analytical layer that can be used for prognostics and diagnostics, and eventually provide info about the reliability of the structure. This framework will be demonstrated for a case study, and that's it. It is for the reliability assessment of a composite flat panel that is approximately 1.6 meters long. Now, a little bit about the framework we will be using. Let's say we have a physical system, in our case, a composite structure that has a SHM system integrated and is able to collect data and store the data it is collecting. Every time we operate a structure, the collected data will be passed on to the asset integrity assessment system. And this system contains 4 main modules. The first module is the damage detection module that extracts damage indices and identifies anomalies in the structure. If an anomaly is detected, then we go to the damage localization module that informs us about the location of the damage. Then we can move to characterizing the defect in the third module and estimate its damage size. And finally, if we have information about the location and the size of the damage, we can go to the final in the fourth module to do a reliability estimation. So we can go through the hierarchy of SHM till final reliability assessment that will drive maintenance decisions. Now, all of this will have to happen very rapidly in the online phase. In order to have a system like this, we need extensive preparatory work, like experimental and numerical model, and we will complete all of this in an offline period. This offline phase will actually include all the necessary steps you need to design and develop the system before its final deployment. So we can start with some experimental campaigns following the building block from coupon to monostringer and to flat panels, so increasing the complexity of the structure. And the first thing we're going to do is collect measurements from both pristine and damaged specimens at different environmental and operational conditions. This will give us an extensive library of signals that we can process to extract compensation factors that we will see later where we need them, and also features and thresholds for those features that will drive damage detection. However, before deploying the system, we need to be able to assess its robustness. So in parallel, we have some physics-based model, mainly finite element models. Here we have models on guided wave propagation that will take information from the library of signals we have collected to calibrate our models and generate a synthetic dataset. Once we have this capability ready, we will use this dataset to estimate the model-assisted probability of detection. So instead of doing hundreds and hundreds of tests experimentally to quantify what is my probability of detection, we will drive these computations from the calibrated models and the thresholds we have extracted. And this will drive the certification of the system. At the same time, we can use the same calibrated models to really assess network optimization and design our network. Once we have all of these things in place, we can deploy our system to the physical structure and pretty much provide information to the first two modules, damage detection and damage localization. For the next two modules, damage size estimation and reliability assessment, we have to follow a similar approach. First, we need to go to our experimental campaign and really extract information about the structural behavior of our material and quantify uncertainties relating to material variability. At the same time, we want to quantify any uncertainties in respect to the operation of the SHM system. So, for instance, how the system interacts with damage. In parallel, we developed two numerical models, a model for structural behavior, here because we have composites, that's a compression after impact simulation really, and a structural SHM model that simulates how waves propagate and interact with damage. In order to estimate the damage size, we follow a fusion process that we will describe later on in order to create a mapping that connects the readings from the sensing network with damage sizes. And this will allow us to perform the third step and the third module with damage size estimation. Now, once we know that we have a damage, the location of the damage and the severity of the damage, we can use calibrated models for for residual strength of damaged composite panels that contain the uncertainty from the experimental investigations and really train some surrogate models that during deployment, they will be able to operate very rapidly and very fast to give us a reliability assessment. And once we have this information, we will be able to advise about the maintenance action. Now, the remaining of the presentation will actually follow these 4 steps, and we will go in more detail of how we actually overcome challenges and the work we've been doing about overcoming these challenges, following the hierarchy of structural health monitoring. Specifically, we will demonstrate the process for a composite flat panel. I had available 3 flat panels that were impacted at different locations, and we were able to collect various SHM information from those panels. All of them were made from the same material, and they were sensorized with piezoelectric transducers to induce guided waves. However, I want to focus your attention on one panel that was impacted at this location only, at the foot of the stringer. This impact generated a disbond between the skin and the stringer. And the whole idea of this framework is to blindly assess our capability to estimate the residual strength of the panel based on the SHM indications. So we will not use any other information other than the information coming from the SHM models. Now, throughout this presentation, all SHM-related information are coming from a network of piezoelectric transducers that excite a guided wave. And as this guided wave propagates and interacts with damage, we quantify some features based on the correlation coefficient. And in order to assess the existence of damage, we do anomaly detection with Mahalanobis distance. So starting with the first stage, the first module, and damage detection. The first challenge we need to overcome is to be able to understand the different environmental and operational conditions and be able to account for them and compensate for them. So, as it is expected, if we have a structure here, a composite panel, and we record some signals from this sensor to this sensor, as the temperature changes, these signals are also affected. And here I have a plot of how the signals are affected for different measurements. We put this panel in an environmental chamber and we change its temperature from -50 to 70 degrees, which is a reasonable operational range for aviation. And so that the differences in the signals are so severe that can easily mask the existing of this defect or create a lot of uncertainty about false positives is an indication. So in order to overcome this, we can compute through extensive experimental investigation compensation factors that are able to alter the amplitude and the phase of the signal in order to go from the original signals to a compensated state where we can see that the effect of the temperature has been removed. And this will allow us to really improve our detection capabilities and reduce false positives. However, quantification of these compensation factors requires a lot of experiments. And the biggest question we need to answer is how feasible it is to collect these datasets. Because as the structural complexity increases of our components, the feasibility to do experimental campaigns actually is reduced. This means that we cannot take a big aircraft and try to get hundreds and hundreds of data recorded from it. So the idea and what I implemented here is to follow the building block and go from simple structure to structure with increasing complexity, and at its scale correct and add additional correction factors that aim to improve the temperature compensation. And I have plotted an example here. So these are signals collected from the flat panel along this sensor pair. And our aim here is to go from this red line that is collected at 35 degrees to go to this blue line that is collected at 25 degrees and try to remove the effect of temperature. If I have only compensation factors from the coupon level applied directly to the flat panel level, we will go to this dotted line. It is close to the blue signal, but again, there is room for improvement. And if indeed we add additional terms that have been collected from further experimental investigation at higher levels, we can further improve our compensation and reach a better agreement between our compensated line and the true signal. And we can observe this improvement in this error plot at different temperatures. And we see how going from no compensation at all to having compensation from coupons and to monostringers and to target structure directly, we can progressively reduce our error. And this error reduction is actually a huge improvement for our detection capabilities. So this process is actually able to reduce how many experiments we need at the big and the final target scales that is difficult to get many experimental investigations by increasing, by adding more and more information from the lower levels and propagating them to the target level. So now that we have a way of accounting for environmental and operational conditions, we need to quantify the performance of our structure and really certify it. The aim here is to really quantify the probability of detection. And the way we can do this is either following a very strict experimental frameworks that have been described in the literature, but because these require many experimental repetitions, another way we can think of the problem is to leverage physics-based simulations in order to assist in our detection, in the computation of the probability of detection. So the model I have used here is a simple model of a composite panel where we can generate and propagate guided waves. And at the damage location, what we can do is we can go and locally degrade the material parameters, and we can do this by the introduction of a fiber damage and the matrix damage parameters. And by degrading these material properties, we can actually simulate the interaction of propagating waves with actual damage. And the idea here is to use some experimental investigations we have done in order to calibrate our model and then use this model to generate more and more damage scenarios. And here we see again the problem of data scarcity. It's not always possible to get very extensive experimental campaigns. It's not possible to get hundreds and hundreds of damage scenarios at different locations in order to characterize your system. So we can leverage our physics-based simulations to aid us in this activity. And the way we can do it here is by training a digital clone that will replace experimental campaigns by calibrating our material parameters and find the combination of material parameters actually that degrade locally the stiffness of the composite panel in such a way that captures all the uncertainties we see in the experiment. And this is what these distributions really try to capture. Now that we have a calibrated model, we can combine it with some thresholds and uncertainties we extracted from our investigation on the effect of temperature on our system operation. And we can estimate how many of these simulated damage events we were able to detect. And we can get a curve for the probability of detection for different temperature differences. Which for us a temperature difference is like also an extra uncertainty that is coming into the equation. Having models like this also give us the option to go much deeper into assessing the structure and identify hotspots where this damage might be missed. And instead of having a global probability of detection, we can actually estimate probability of detection at different locations of the structure. And here we see some hotspots over here where a damage might be missed. And this is because the sensor configuration is actually operating on these pairs, and at the gaps, let's say, our probability of detection is reduced. At the same time, we can investigate what happens if a sensor fails. And we can see that in this region, our probability of detection goes to 0, but the rest of the structure is operating nicely. So putting it all together, we have a way of addressing temperature differences. We have showed that we have a robust system. We are ready to put it into action and try to detect damage into our flat panel. Here I have plotted all of the damage events that are available. And on these figures, we see the extracted damage indices for a sample damage. So for each investigation, we extract the damage index along each sensor pair, and we extract features based on the standard deviation and the mean of these damage indices in order to do anomaly detection. From the investigation on the temperature effect, we can calculate a threshold that ensures a 99.5% probability when we have a temperature difference up to 25 degrees. And what we see here is that every damage event in the flat panel we have was actually correctly identified as a problematic signal. And specifically, the case we are interested in as a blind test, this one is over here, which is clearly identified and separated from our threshold. So now that we have detected the damage, the next step is to localize it. So using the same features and the same signals, we have found that the best results were able to be identified by combining two very common imaging algorithms, the delay and sum algorithm with the rapid algorithm, where when we combine these two, we are able to get very good estimations about the location of the damage. And this algorithm pretty much give us heat maps that provide a visual indication about where damage is. So if we apply this to our flat panel, we can complete also the second module of our integrity assessment system, and we can get a heat map of how and what exactly is the location of the damage. Here I have such a plot in order to illustrate. And on the right side over here, we see the localization estimates and their uncertainty for each of the available impact events. And we can actually see that even when we have a 10 degrees temperature difference, our localization algorithms can quite accurately estimate the true location of the damage. So we have detected the damage, we have localized the damage. The next stage is to characterize the damage and assess its size. But we have to be careful because the sensor we are using in SHM, they cannot measure damage directly. All these measurements are actually indirect measurements. We extract some features and we try to correlate these features with specific damage scenarios. So we want to be able to capture all the underlying uncertainties in this mapping between the damage feature and the damage size. And the way I have developed this module is to leverage a multi-fidelity approach and leverage both numerical and experimental observations to improve our accuracy in the predictions. So essentially, we can write down our relationship that connects a damage area and a damage location, that's our input vector X, with the damage features we are getting from the damage indices. This relationship can be divided in 3 terms. The first term is a low fidelity term that is trained using numerical data only, and we call this low fidelity because the numerics have some physics that are not captured perfectly compared to a real experiment. Next, we have a discrepancy term that pretty much tries to capture all the uncertainties and the discrepancy between experimental observation and numerical system. And finally, we have some measurement noise from the monitoring system. Essentially, if we manage to come up with a relationship like this, we can try to answer the following question. If we get a damage feature from our first module, the damage detection module, along with an estimate on the location of the damage, can we infer what would be the damage area that would explain these two indications? And the way we can do this is by casting this problem into a Bayesian formulation and really try to identify a distribution or the damage area parameter that would explain our observations we are getting from the SHM system. For the numerical model of this multi-fidelity assessment, we have developed a very accurate simulator of wave propagation interaction with dish bond damage. We can see here that dish bond is simulated really by releasing locally the tie constraints between the skin and the stringer in the elements of this flat panel. And this gap between the two structure actually resembles the dish bond caused by the impact damage. As waves propagate and pass through this location, we are getting reflections and attenuation that are caused because of this defect. And we use this model to generate a numerical data set of impact events at different locations with different sizes. And the idea is that we can use this data set of numerics to train the low fidelity simulator, a surrogate model for the low fidelity, and then use some experimental investigations in order to account for the discrepancy between the real structure and the experiment, so going from here to here. In total, we have 4 impacts that caused delamination between the skin and the stringer, and these impacts will be used for the training phase. So with this in mind, we are ready to estimate the damage size. Here on the top of the slide, I have some slices of the response surface of the final multi-fidelity approach. And effectively what we have is what we expect to be the damage feature, the expected damage feature for different damage sizes and different locations in the structure. With blue, we have only numerical simulations. With red, we have a corrected response after we observe the experimental data, and we improve our estimations with the discrepancy there. In reality, we can do a leave-out cross-validation result and try to estimate for each case what the system would indicate as a damage size. And again, I direct your attention to this case, which is our blind test. And we can see that without observing, of course, this impact event, observing only the other 3 impact events, we were able to get a very good estimation of its damage size with a mean error of about a little bit over 10%. And the interesting thing here is that we were able to get such estimation using, in reality, only 3 experimental observations. This would not have been possible if we had not combined our experiments with numerics in order to create to capture the, let's say, global behavior from the finite elements and refine the global behavior with our 3 experimental data points in order to make our estimations even better. So after having quantified the damage size, we can move to the final stage, which is predicting the residual strength. We know there is damage, we know where the damage is, and we have an estimation of how big the damage size is. So what we need to answer now is what effect this has on our structure. To be able to answer this question, we start our mechanical building block really, and we go from coupon level, where we try to quantify material variability and create a finite element model that is validated at the monostringer level to make sure we are able to capture accurately the failure of the composite, and then we use this model directly for the flat panel case in order to provide residual strength and reliability estimations. At the coupon scale, we are extracting variability at different material properties, and after a parametric sensitivity analysis, we identify that the 2 main parameters that affect our residual strength is the longitudinal, along the fiber, let's say, stiffness, and the longitudinal compressive strength. We didn't want to have too many calibration parameters here because our design space would become too intricate to navigate and explore. Now, using this material variability, we start by constructing a finite element model that captures that simulates an impact, damage after impact, and then compression after impact to simulate the final failure of this monostring. And we can see that the numerical investigations can capture the same mode of failure as observed in the experiment. Now, in order to make our simulations a bit more computationally efficient, instead of simulating the whole process of impacting the structure, damping the vibrations, and then performing the compression step, we avoid the impact step and directly induce damage to the cohesive elements between the skin and the stringer in order to make our simulations go faster. This is going to be very important in the next stage that we actually simulate the larger structure. And from the results, we see that we are able to capture quite nicely the response observed experimentally with the variability from the coupon scale that has been propagated to the final monostring. So using now this validated model, we go directly to the flat panel. Locally, we start by simulating different scenarios of damage sizes by removing the cohesive elements and creating damages of different shapes and size at this location. And we see how it progressively we damage really the bonding between the skin and the stringer, and we extract the final failure of the structure. Our simulations again predict the same mode of failure as the experiment, having buckling after the T-bond of the skin and the stringer. The skin is buckling, leading to the final failure of the pack. So we have information about the existence of the damage, the location of the damage. We have a model that is able to give us indications about the residual strength of the panel for a given damage size. In the final stage, in the residual strength assessment, we can combine all of this information and effectively train a surrogate model that is able to quickly provide us estimations of what the residual strength is going to be for different cases of damage size. From our SHM indications, we know an estimate of the damage size. So essentially, we can go there and start sampling really our Gaussian process. We can go here and start taking samples from this surrogate and compare the samples, the residual strength that we expect to have to the true residual strength that the flat panel actually exhibited during the experiment. And we can see that our final answer is within 5% of the true value and the mean estimate. So overall, we were able to predict quite accurately the residual strength of the panel, driven solely by indications by a numerical model. And the important thing here is that once we have estimations about what is the current strength and the current residual strength of the panel, we can compare it with design values. So, for instance, what is the expected load during the next mission profile, and really answer the question, what is the reliability of the structure? Is it expected to fail within the next mission? We need to do any corrective actions. We can keep using it or not. And we can compute this probability with different methodologies, starting like first order and second order reliability assessment, or even with brute force like Monte Carlo sampling, and get the final answer that an operator will use to drive his decision making. So as a conclusion, I would like to emphasize four main parts. First of all, how important it is to adopt hierarchical approaches, because it's not possible to perform that many experimental investigations at large scale and complex structure. But following scalable methodologies, we can really prepare our data sets and inform from lower scales to higher scales our system in order to be able to deploy it for a real-world structure. Furthermore, it is possible to, leveraging some machine learning principles, it is possible to capture uncertainty and systematically propagate it to final estimations. As we saw, for instance, in the assessment of damage size, we were able to capture both the uncertainties and predict quite nicely the size of the damage. The advent of digital twinning, we can close the loop and really connect the sensor information to final probabilistic and reliability indicators. And lastly, with this, by closing this loop, we can actually predict, for instance, in composites, residual strength. In metallics, we could expand this to do some remaining useful life and assess crack propagation and how long it will take for a crack to propagate to an unstable size and so on. So a little bit about current activities and future directions. Currently, we are working on a Horizon project called Avatar, where the idea is to extend this framework and extend this research I've been developing in order to capture not only assess if there is a structure, if there is damage, but really provide a holistic solution, including sensor technologies, data acquisition technologies, processing and visualization interfaces that will actually inform in real time the user about the state of the structure. We are working on a composite drone and a metallic aircraft. And an additional layer to the modules we discussed today, we are aiming to develop, is to develop also the capability to monitor the time history of the structure and extract specific information of how the structure has been loaded. So I don't know, these are supposed to be some animations that we could see that the wing is vibrating, and at the same time, our digital twin is able to reproduce this vibration. And the idea is that with wireless data acquisition and sensor systems, we can actually predict stresses at specific hotspots that will be used to drive, for instance, crack propagation activities and assess remaining useful life. Thank you very much for your attention, and I'm open to any questions.
Thank you very much, Ilias, for the very comprehensive presentation. I think you've given us all the components covering every aspect of the digital twin building. So I think it's very, very interesting. We have quite a few questions from Ahmed Al-Jaruf from Aramgora in DC. Ahmed, did you maybe want to ask yourself? Yeah, go ahead, Ahmed.
Okay, now it works, I guess. Hello?
Hi.
All right, okay, good. You can hear me, right?
Yes, yes.
Yeah.
All right, thanks, Ilias, for the presentation. It kind of gives me memory when we used to go to the Imperial College for AI-related seminars, so that's great. I'm actually from Aramco. I'm part of the R&DC, Research and Development Center, that we are collaborating with KAUST as part of ENERCOMP that was mentioned at the beginning. I have few questions, and they are a mix of AI, data analytics, simulation, surrogate models, and the efficacy also of the sensor that you're using. So it's a mixed bag, which I have listed in the chat. If you can see them, we can go from the top. The first question I had in mind was when you had, I think in your second or third slide, you went through the flow process, one earlier maybe. Yeah, this one. So you went from damage detection to localization and then size estimation. So it seems for you guys, the location is more important than the actual size of the damage, whereas in other application, maybe the size might have a higher priority, because if it is big or small enough, then basically the location comes also as. So the question I have, is this a cascaded priority, or is it kind of have equal priority 2 and 3?
I would say it's application specific. So I would imagine, for instance, in a structure I don't know, that has a strength concentrator, and you know that the crack will initiate from that point, you pretty much already know the location of the damage. So maybe the localization doesn't have that much of an effect on your estimations. But if I can jump a little bit further to because this will allow me to better explain why it is important here, the localization before the damage size, is because of the application we are actually considering. So for me, I will have a damage in the interface between the skin and the stringer. So a damage at this location and a damage at this location will provide me different signatures. So in order to be able to use later on in my multi-fidelity model to capture what is the extent of the damage, I first need to know where the damage is in order to search, let's say, for those signatures. And this is why it is important to first identify its location and then its size, because the location will be as an input for me for the damage size estimation. If I knew that for some reason, I don't know, I have a bolt over here, so I expect the lamination to initiate at this location, then I could even skip completely the localization step and go directly to damage sizing. So essentially here, for instance, we didn't simulate damages only at this location. We simulated damages at myriad possible locations with different shapes and different sizes. And then we did our estimation.
Okay, fine. So this is a good clarification. Now, the second item is the sensors that you guys are using. Are these an off-the-shelf sensors
Yes.
or?
Yes.
Okay, so
For
you
all,
have
for
no
all,
control. Okay.
yes, for all results I presented today, they were generated using off-the-shelf piezoelectric transducers and off-the-shelf data acquisition systems. So the data acquisition systems are from NI, but we have developed our own internal, let's say, codes for the interrogation. But the hardware is everything is off the shelf. Actually, we are currently in the process of producing our own sensors with DTI, the Danish Technological Institute, and the aim here is to produce printable sensors. But for the results you saw today, everything is using commercial PCTs.
And you're going for printable because flexibility, I guess. But I have another question on that. What is your range of sensitivity you're after, as a percentage?
When you say a range of sensitivity as a percentage,
So what are you, like, if this is a piezoelectric sensor and then you are artificially inducing a defect, then you're looking for a certain signature to be, recorded on the sensor. So how small that needs to be for you to kind of say, like, okay, I have like a reliable register here. I'm not sure if I'm explaining myself well. Okay.
Our reliability will actually depend a lot on the operational conditions in our case, because it's for aviation. So if I assume I have perfect conditions, we will be able to detect damages down to 4 millimeter in radius for a plate with this setup. For sensors, I don't have the distances here. This is approximately 300 by 500, I think, the dimensions of this plate. Obviously, the sensitivity will change as you go to more complicated structures like this flat panel. But what we have observed here is that you have to first identify what is your critical damage. So for instance, for us, a damage on the skin over here or over here does not really degrade the strength of the structure, while a damage on the interface has a very pronounced effect. And this is why I use this as a case study to be able to predict it. And our prediction capability to that, I don't have it. I don't remember it exactly, but I would say it was something like the estimation was something like 100 to 200 millimeters square, an area of, I don't know, 10 by 10 or 10 by 20, something like that would be the minimum detectable damage size.
Okay, so this is in relationship to kind of pretty much hardware related. If we move on to the kind of software related questions, I have three, but I will be very short just to give time for everybody else to ask questions. I will probably start from the bottom. Now, I did look into surrogate models for different applications back in the time when, AI started to kind of make splash on the scientific community. Now, AI is 10 years old, more or less. But the main question is, usually whenever you rely on a surrogate model, then you are running the risk of accumulating error, right? So you have a compounded error because the surrogate is done by simulation and the simulator itself is not as accurate as the experimental results. So you kind of going in loops. So why don't you just make use of the simulation directly, assuming that that simulator is also accurate in relationship to the experimental results? When I put my question, I did put it before you had a slide where you were showing the experimental outcome and the simulations with that kind of standard deviation between them. But it
You're
struck
talking
me,
about here.
yes. So is this an experimental versus simulations, right? This is what you're saying by the mean
Yes.
numerical. Okay.
Yeah.
And so if your simulator is as good as the experiment with the margin of error, why are you building another surrogate on top of that simulation?
Because it comes down to computational cost. So in the end, in the process, when you operate a system like this, you need to be able to make to do the complete assessment in a matter of, I don't know, maybe minutes or something like that. You don't want to tell the operator, okay, wait a couple of days to run my simulations. For this
I
scale,
understand. Yeah,
it would be feasible, but each simulation at this scale was about 16 hours, each simulation. And we tried our best. I tried our best using Imperial supercomputer to reduce it as much as I could. So let's say we're at this stage. We have a probability distribution of my damage size, and I want to sample this probability distribution and run simulations. You have a sample coming from your damage size. You have another unknown, which is your material parameters. So you would need to sample this many times in order to be
No,
able
I
to
understand. Yeah, and usually the simulation time is also a prohibitive kind of measure. But really, like I would be cautious about that, specifically when it comes to industry. Your surrogate model will have it will suffer from accuracy deterioration. So maybe I don't know if you have a plot here to kind of compare the outcome from a surrogate model on a data set that is not used for the training of that model. If you're using deep neural networks or other means in comparison to a native simulation, and how does that compare?
Yes, so in reality, I have it over here. I'm using Gaussian processes specifically. If I had a model, I agree with you that if I had a model that I could run it in let's say, a reasonable amount of time, I would not use any surrogate. I would use a model directly. But here we can, this is the comparison. The blue lines are the outputs from the surrogate. The black crosses are the real estimations that were not used during training. So this is the comparison between the surrogate and the, let's say, the direct simulation of the of the structure. But sometimes it comes down to pure computational cost, that it is not feasible to have a very complex structure and run it in real
No, I
time, let's
understand.
say.
Yes. But this is exactly the point I'm trying to say. So if you look here at the standard deviation, if you quantify it and then you multiply this by the other standard deviation that you had from the numerical against experimental, then basically you are, doubling your quadrupling actually, like it's squared, if not more, your error. But just like a food for thought. I'll stop here and leave the floor for others to ask questions. Thanks a lot, Ilias.
Thank you.
Thank you very much. We also have one question from Omar. Omar, if you yep.
Hi, can you hear me?
Yeah.
From what I understood, your main focus is currently damage detection and localization. So when it comes to damage prediction, is this something that you are currently working on? I understand that it might require even more sensitive sensors to pick up smaller signals, more post-processing to like have a future prediction of the state when you extend this trend, or even some knowledge about the operation, the next operation steps, so you can predict how it will affect the current state of the structure. So are these things that you are currently considering, and how you can do so?
So I'm not sure I understand what you mean by damage prediction.
So, for example, if
yeah.
you can predict that given the current behavior,
Mhm.
it seems that if we continue under this pressure or something, there will happen a damage at this certain location. So you can take some action or lower some values to prevent damage, not just respond to it after it occurs.
Okay, I see. It is a little bit different, the setting, because the damage I'm considering is stemming not exactly from operation, but also from the use. So, for instance, this is a damage that created because of an impact, of an external impact. And not due to, for instance, the stresses that were developed during operation. But what you are discussing, yes, it is something we are doing currently in the current project I mentioned, that we are recreating stresses and strains at specific hotspots that we know damage will initiate, and try to capture both the initiation phase and the crack propagation phase, let's say, in order to characterize the full life cycle of the operation of the structure. I don't know if this answers your question.
Yes, thank you. This is clear now. You also mentioned the printed sensors. So how would they be different from your off-the-shelf ones? How would that be important for your future work?
So in general, the capability of having automation is important for SHM because it can reduce a lot the integration cost. So imagine you have a flexible layer, like I don't know, like a piece of material that you can go on your structure, just stick it on it, and start collecting data. So that's the holy grail, let's say, instead of going there, trying to put sensors, put cabling, and so on. If you are able to print the sensors, we are already able to print tracks, conductive tracks. If we are able to print the sensors as well, this will give us, for instance, the flexibility to create very lightweight systems, avoid as much as possible using cables, and contribute a lot to keeping the structure as lightweight as possible.
Yeah. Thank you very much for mentioning this, because we are also here working on printed electronics, so it is good to have a confirmation about how the future of SHM is going to be shaped like. Thank you for the seminar in general.
Thank you very much.
Thank you so much, Ilias. Very interesting presentation. Thank you.
Thank you, Ilias, for giving the presentation. Very comprehensive and very interesting. And thank you everyone who has joined. I hope it's very useful, and I think we're looking forward to more webinars in the future.
Thank you very much for the invitation. Bye bye.
Thank you, LD, for taking care.